Kia ora and welcome to video 24 in the series Insightful Integration. This is our penultimate problem. This one here is similar in nature to yesterday's video by Wesley, in that it involves projectile motion. It is a challenging problem, and I remember setting this a few years ago to some students in my class at the time, and they found it very challenging. There are different ways of attacking it. We're just going to look through one of those in this video. I've picked the best solution. But of course, if you find an alternative way, maybe comment below and let us know about it. Okay, so first up, let's describe the vertical movement of the cannon. So if we draw a picture here, the cannon is on some platform. Excuse me on my terrible drawing of a cannon. Then we shoot it off at some height h, and that's the initial height of the cannonball, and gravity is the thing that's acting on this cannon. So vertically, acceleration is equal to negative 9.81, which is g, so my g is negative for this. If we anti-diff, the vertical velocity is gt plus c, a linear function of time. C is the initial vertical velocity, so if we were to zoom in kind of on what is happening here, we've got the cannon being shot off at some angle alpha at some initial speed. So we could say v max to go the furthest. So therefore the initial vertical component of that velocity is v max sine alpha. And so if we sub that in at t equals 0, we get v equals v max sine alpha. That's our c value. So now we've got velocity function gt plus vmax sine alpha. Okay, and then the last thing is we need to antidiff that again. If we antidiff velocity, we get displacement. We're talking about vertical displacement, so we'll use y equals the gt squared over 2 part, so linear function antidiffs to a quadratic. This vmax sine alpha term differentiates to a linear term. It's initially constant, put a t at the end of it, and then we get some other constant which we're going to call h, the initial vertical component of the cannon. So that describes the cannonball vertically. Now we're assuming no air resistance, so in terms of horizontal movement, our acceleration is equal to 0. So just make clear that this is vertical and this is horizontal. Acceleration of 0 means that the velocity not vertically, but the velocity horizontally is a constant. That's v max cos alpha. Going back to our little triangle, when it starts off, the cannonball is shot at an angle of alpha, then the vertical component is v max sine alpha and the horizontal is v max cos alpha, and that doesn't change throughout because there's nothing slowing the cannonball down horizontally. If we antidiff that one more time, then we've got our x, our displacement of the x direction is v max cos alpha times time plus c, but c is 0 because we're going to treat this as x equals 0 and this is x maximum, the value that we're trying to find. Now at this point I dropped all the v maxes and just called them v for simplicity. Not to be confused, of course, with that v there, but we're not needing that anymore. So I want to maximize x. It's a differentiation type question, and the first thing I need to do is actually find an expression for y in terms of one variable. So if I take my equation for y and So just rewrite it without the v max. I can make t the subject of this equation, and that will eliminate the t value. So if I do that, making t the subject of that gives me t equals x over v cos alpha. And then I can sub that into my y expression. Y equals g over 2 x over v cos alpha squared plus v sine alpha. Again, x over v cos alpha goes in for t plus h. Now I've got y in terms of just x and alpha. Remember that v is a constant. It's the initial velocity of the cannon firing at maximum speed. This looks like an absolute mess, and how am I going to differentiate it if it's still got two variables in there? But what we're trying to do is find the maximum value of x when y is 0. So if I make y equals 0, that's when it hits the ground. And then I also tidy up this expression here, because I've got g over 2v squared, I've got x squared, and then I've got cosine alpha all squared there, but in the denominator, so technically that's sec squared. The next term, I've got sine over cosine there, and the v's cancel, so I've got x times tan alpha, and then I've got plus h. Now actually, looking through some of the solutions to this problem, I said from the outset I'd just cover one, but at this point in time you can actually use the discriminant, because it's a quadratic equation. It's a quad in tan of alpha, because we can replace the sec squared part with 1 plus tan squared, and then write it as something like something tan squared plus something tan plus something equals 0, and then use the discriminant. The discriminant needs to be greater than or equal to 0 for there to be a solution for this problem, and it turns out if you do that, the discriminant will have just x's in it, and you can solve that inequality to find the biggest value of x that's possible. So I didn't see that sort of approach until later when I was looking through other answers to this problem. So if you want to continue from there using the discriminant, it's so much easier, but I didn't notice that, so I'm going to continue with my differentiation approach. Okay, so I'll make this equation here, and I also didn't think to make sec squared 1 plus tan squared. Okay, so I want to differentiate this. So I've only got two variables left. I've got x and alpha. X and alpha are the two variables, and g and h are constants. And I could make x the subject of this equation, right? I could make x as a function of alpha. That would require solving a quadratic. It would get really messy. And then I'd be looking at a graph which is x depending on alpha, and I want to find the biggest value of x. So it's a differentiation problem making the derivative equal 0. But when you can't rearrange an equation, or it's really tedious to rearrange it, implicit differentiation is your friend. So I'm going to implicitly differentiate the equation that I've got there, which I'm going to call triangle. Implicitly differentiate triangle. The reason I'm calling it triangle is because I'm going to come back to that later using that equation again. Okay, left-hand side, differentiating 0, 0. Differentiating this sec squared term with respect to alpha. Okay, we have to be careful here. We've actually got two parts. We've got this dude here, which is a function of x, multiplied by this dude here, which is a function of alpha. It's a product rule we need. Fortunately, g over 2v squared can just sit in the front because it's a constant. Now we differentiate x squared. We're differentiating with respect to alpha here. So that's 2x multiplied by dx d alpha times sec squared alpha. And then the next term is the derivative of sec squared alpha with respect to alpha. Well, that's sec alpha all squared. Differentiates to 2 sec alpha to the power of 1 multiplied by the derivative of sec, which is sec alpha tan alpha, multiplied by x squared, the first part of the function. And then we've also got to differentiate x times tan alpha using the product rule again. The first part is the derivative of x with respect to alpha. Okay, that's just dx d alpha multiplied by tan, and then plus the derivative of tan sec squared alpha times x, and then h disappears. Derivative of h being a constant disappears. So we've got this absolute mess. Now we could make dx dA the subject of the equation, but we're trying to find the biggest value of x for some value of alpha. So dx dA is actually 0. So when we make dx dA equals 0, or dx d alpha, sorry, the first term disappears in that bracket, and the first term in the second bracket disappears as well. So we end up solving this equation. Okay, has that worked for me? So I got rid of that whole term there, got rid of that whole term there, and okay, that's an equation where I can factor out some stuff. The 2's also cancel. I can factor out an x, and I can factor out a sec squared. So x sec squared, both of those can't be 0. And then the first term needs a tan alpha, another x, and also a g over v squared. And then the second term just plus 1. And for that to equal 0, because the first part can't equal 0, it means that tan alpha times x times g over v squared must equal minus 1. Setting that bracket equal to 0, and then remember we're trying to find the maximum x, so let's make x a subject of that. We've got x equals minus v squared over g tan alpha. So that tells us what the maximum value of x is, assuming it's a maximum. I haven't actually proven that. I really don't want to differentiate that thing again. But that value of x, don't get confused by the fact it's negative, because g is actually negative, so that is a positive number. But that depends on alpha. So what that's saying is that the maximum value of x depends on alpha there. We don't want that. We want the g, which was from the original problem of gravity, and we want h in there somehow. What you could do is like set alpha to be equal to 45 and say that that's the biggest value there. But if we go back to our triangle equation, which I said I was going to come back to, hence why I called it triangle, if I just bring that down here, okay, let's get rid of all the highlighting. That didn't work. Might as well just rewrite the damn thing. Almost. Okay, so we're solving this equal to 0. Now we know that x apparently is equal to this, so we can rearrange that to get rid of the alphas, because that's telling us that tan alpha is equal to minus v squared over x times g, or tan squared alpha is equal v to the 4 over x squared g squared. Now both of those can be subbed into this triangular equation with a triangle next to it, because we know that sec squared is equal to 1 plus tan squared. So 0 g over 2v squared x squared multiplied by 1 plus tan squared, which is this, plus x lots of tan alpha. Well, x lots of tan alpha is just, if you look at the tan alpha equation, the x on the denominator will cancel, so we're left with minus v squared over g plus h. And then if we just tidy this up and solve for x, there's only one term that's got an x in it, gx squared over 2v squared plus, and it's expanding that bracket, the g, one of the g's cancels top and bottom, the v squared cancels, so we're left with v squared, The x squareds also cancel over 2g minus v squared over g plus h. Okay, we can put those second and third terms together. It's just a half minus a whole, so make that like that. And it's negative v squared over 2g. And then move everything to the other side. So we've got v squared over 2g minus h. Then cross multiply this thing, times both sides by 2v squared, and divide both sides by g. Told you this was a hard problem. Okay, cancel the 2's. We've got v to the 4 over g squared minus 2v squared h over g equals x squared. Now I want to square root that. X is a positive number, so we take the positive square root, and we can put both of those dudes together. V to the 4 minus 2v squared gh. I add another g into that second term so I can divide both of them by g squared. Factor out a v squared out of the numerator, and then outside of the square root is a v. Factor out the g squared as well out of the square root is a g. And we're left with v squared minus 2gh. Remember that v was v max. So that is apparently the maximum value of x. Actually, I lie. I should have the negative square root there because g is negative, and therefore I want a positive number out of that thing. But that there is the maximum value of x, and you could make a Desmos graph to check that, because you can play around with different values of alpha using the parametric equations which we started with. Okay, use this equation here as your y value, this equation here is your x value. Graph a parametric equation by, I'm not going to rewrite the whole thing, but graph it as x comma y, where both x and y are functions of t, and then let alpha and vmax be constants that you can slide around, and then look at where it hits the ground by plotting and seeing, where it hits there, and then looking at how this value changes depending on what alpha is and what vmax is, and you'll find that that maximum value is the value of x that we've just found. Hopefully you found that really interesting, and we'll catch you for tomorrow's video, which is the last one in the series.